All right, so today we're going to complete chapter 4 on cyclic alkanes. All right, so to be clear, an alkane like hexane would be this example here. This is our alkane. My specific example here was hexane. A cyclic alkane is if those carbons are connected together in a ring-like structure. So if I take those same 6 carbons, but I create a ring here, this is a cyclic alkane. And whereas the straight chain alkane was named hexane, this is now cyclohexane. All right, so first thing we're going to do is we're going to update our nomenclature rules for these cyclic compounds here. And I'm going to kind of crash course through it here because it's only a few little additions, but I did create a longer video with more examples that's posted on Canvas that you can watch if you're having trouble with your nomenclature of cyclic alkanes. All right, so how do I get my name here? So I got the same 4 steps that I always have. What's our first step in nomenclature? Yeah, parent chain. All right, so step 1, same as always, parent chain. All right, if we're going to update our rules for our parent chain here. All right, longest continuous set of carbons, that's what we were using before. For cyclic alkanes in particular, the ring is always the parent chain. All right, now I'm lying to you a little bit. There are special cases where if you see a structure with a ring in it, the ring isn't the parent chain. But I'm going to pick my battles here in this course and not try to teach every exception under the sun. So as far as we're concerned, if we see a structure with a ring in it, that ring is always going to be the parent chain of that molecule. All right, so now we got to update our functional group here. How do we name our cyclic alkanes? For alkanes, it had that A-N-E ending. For cyclic alkanes, you're going to start with the word cyclo. Then you're going to use that number of carbon prefix, the same ones that we saw before, prop, but, pent, etc. And then since they're cyclic alkanes, they have that same ending, A-N-E. So when I look at this molecule here, I know that this 6-carbon ring is always my parent chain. So that's how I got this as cyclohexane. Let's do it in orange. All right, well now let's do an example where we're going to tack an alkyl group onto that parent chain, onto that ring. Okay, so first of all, I kind of gave it away with what I just said. What's my parent chain here? The ring, always the ring, right? So right off the bat, I know that these 6 carbons right here, my cyclohexane, is my parent chain. So check, check, we got step 1. What was step 2 in our nomenclature? Substituents. All right, and here we got nothing new. We just have our same alkyl substituent, 2-carbon alkyl group. What would I call that? An ethyl group. So for substituents, we're going to simply say nothing new. And what was step 3 in our nomenclature? Number them, right? So now we got to number our parent chain. And here there's actually nothing new either, but I am going to reiterate what those rules were. All right. We want the lowest number in the name. And this is really what makes cyclic alkanes a little bit different than straight chain alkanes. For straight chain alkanes, there were only 2 ways that you could number it, from one end to the other or back the other way, right? For a cyclic alkane, I get to start wherever I want. And if I want the lowest number in the name, which carbon am I going to start numbering as carbon 1? The one that has that substituent, right? So this is going to be carbon 1 over here. Now, if I were to pick up that substituent and move it over to a different carbon, I put it over here instead. Does this carbon stay number 1 over here? No, I'm just going to start numbering from over here instead. Okay, so this is a big difference. We number, we want the lowest number in the name. For 4, when we assemble, if there's only one substituent on the ring, as in the case here, we know it's at carbon 1, so we're not going to bother putting that 1 into the name. All right, so for what are called mono-substituted cyclic alkanes, we're going to omit the locant from the name. So instead of being 1-ethyl cyclohexane, this is simply ethyl cyclohexane, all one word. All right, again, we omit the locant from the name. All right, we can just note if there's more than one, we do include the locant. If I had more than one ethyl group on this ring, for example, I'd have to indicate how far apart they are. Are they right next to each other? Are they 2 carbons away? What is it, right? So then all of a sudden I do have to include it in the name. But this is our updated list of rules here for our cyclic alkane nomenclature. Again, going through it kind of fast. There is a video that you can watch on Canvas that has a few more examples. All right, we're going to do 2 more here just to make a point. We'll do 1 more and then we'll introduce a new concept. Let's use a different ring. All right, everybody take a second and name this molecule for me. All right, what's my parent chain here? The ring. All right, so look, even though this substituent right here has more carbons, the ring is always my parent chain. My parent chain is cyclopentane. That makes this a hexyl group, and this one carbon group over here a methyl group. So then I'm going to number my parent chain. All right, I want the smallest number in the name, so I can either go this way or I can go this way. All right. Sometimes students are like, oh, is it clockwise or counterclockwise? There's no rule about clockwise or counterclockwise because these rings are 3D objects. Clockwise, if I'm looking at it this direction, is counterclockwise if I flip it over. And it's got to be the same if I'm naming this unique molecule right here, right? So there's no clockwise, counterclockwise direction. The whole idea is to put the lowest possible number in the name. If I use my blue numbering scheme, it's a 1 and a 3. If I use my red numbering scheme, it's a 1 and a 3. So I have a tie. What am I supposed to do? Break that tie with alphabetical order, right? So just like we said before, again, there's no new rule here, but maybe we should emphasize lowest number in the name, and we break our tie with alphabetical order. Exact same rules as before, but we're going to see a lot more ties with these ring structures, so it's something that's important to keep in mind. All right, so I'm going to pick this one here, my red numbering scheme, because my hexyl comes first in alphabetical order. So 1 hexyl, 3 methyl, cyclopentane. Cool. All right. So now let's revisit this idea of the physical properties of these now cyclic alkanes. All right, so what about polarity of these cyclic alkanes here? What do we think? Polar, nonpolar? Nonpolar and very nonpolar, just slightly nonpolar. Very nonpolar. They still only consist of carbons and hydrogens, so just like alkanes, these are very nonpolar. All right, boiling point, so very nonpolar. I guess we can say only dispersion forces. So if they're very nonpolar and only have these dispersion forces, they also have very low boiling points. All right, but we are going to note this important caveat here. Our cyclic alkanes also have more surface area than our straight chain alkanes. Okay, it turns out that when you take those carbons and connect them together, you create a little bit more surface area on that molecule compared to that straight chain alkane. And if they have more surface area, what does that mean about the dispersion forces between cyclic alkanes compared to their straight chain alkanes? Are they stronger or weaker? Stronger, right? Dispersion forces are proportional to surface area. So that means we also have stronger dispersion forces than our straight chain alkanes. So if I'm comparing hexane and cyclohexane, which one's going to have the higher boiling point? The one with the more surface area, that's cyclohexane. All right? So as a consequence, they have higher boiling points than their straight chain counterparts. And not by much, maybe 5, 10 degrees more or something like that. But nonetheless, a consistent trend that we see. If you take a straight chain alkane, butane, versus its cyclic counterpart, cyclobutane, that cyclic compound will have a higher boiling point. All right. Another physical property that we talked about was our appearance and odor. And we're simply going to say that these are the same as our alkanes. Usually clear liquids with that gasoline-like smell. Unlike straight chain alkanes where we can make really long ones that are like 18 carbons long, you're not going to see an 18 carbon cyclic alkane. All right, we'll talk about chain length here in a little bit, but it turns out that only those sort of 5 and 6 carbon cyclic alkanes are the most common. Sometimes you'll see ones a little bit smaller or a little bit bigger, but we have a much more narrow range of cyclic alkanes that we're going to see. All right, and then lastly, again, the topic that usually we spend a lot of time on are reactions. Just like alkanes, the only real reaction that we have of our cyclic alkanes are combustion reactions. All right, so physical properties, kind of like you would expect, same as our alkanes, with this one exception that we want to note, which is that they have more surface area than their straight chain alkanes. And let's say, we want to just note, with the same number of carbons. So I can't really compare butane to cyclohexane. Actually, that would be an easy one. I can't compare cyclobutane to hexane very easily, but I can compare hexane to cyclohexane and say cyclohexane has more surface area. Cool. All right, so now we're going to get into sort of the bulk of our discussion of these cyclic alkanes. Kind of like alkanes, we're going to use them to talk more generically about molecules and how they're shaped and how they're structured, right? We used alkanes to talk about that tetrahedral geometry. We're going to do something similar with our cyclic alkanes here. First, we're going to use this to introduce these different types of what are called isomers. All right, so isomers, there's two types of isomers that we're going to introduce. The broadest class of isomer in organic chemistry is what's called a constitutional isomer. Or sometimes a structural isomer. Okay, a constitutional isomer, or rather a pair of constitutional isomers, these would be molecules with the same molecular formula, but different connectivity of atoms. So they have the same number of carbons and hydrogens, for example, but the way that those carbons and hydrogens are connected together are different. So an example here would be butane, which has a chemical formula C4H what? 10, right? It's a saturated alkane here, C4H10. And this molecule here, 2-methylpropane, has that same C4H10. So this would be a pair of constitutional isomers here. Right? They have the same molecular formula, but the way that the atoms are connected are different. One easy way to spy a pair of constitutional isomers is to go in there and apply your naming rules to those molecules. Right? These will have different names. So again, this was butane, and this was 2-methylpropane. That different connectivity of atoms leads me to name these compounds differently. All right, and importantly, they will also then have different physical properties. All right, as we said, when we add a branch point to our molecule here, it decreases its surface area. So we would not expect these two compounds to have the exact same boiling points. They'll probably be pretty close, but they're not identical, right? So distinct molecules, but they share that same molecular formula. That's what we call constitutional isomers. All right. The next type of isomer that we're going to introduce are what are called stereoisomers. And if you look ahead on the schedule, you'll see that next week is all about stereoisomers. We're going to introduce one type of stereoisomer here today, and then we're going to talk a lot about it next week as well. Stereoisomers. They are also constitutional isomers. They have the same molecular formula. And they also have the same connectivity of atoms. Where they differ is in the spatial arrangement of those atoms. All right, there are two types of stereoisomers that we're going to talk about. One type today that we're going to introduce are what are called cis-trans stereoisomers. These are the ones that our cyclic alkanes have. That's why we're going to introduce those. We'll get to it in the future. Alkenes also share these same stereoisomer properties. And then the ones that we're going to talk about next week are what are called chiral stereoisomers. And we'll get to that next week. We're kicking the can on that one. All right, so again, what we're going to focus on are our cyclic alkanes and this concept of these cis-trans stereoisomers. So what do I mean by that? Okay, so let's do an example here. Everybody take a second and draw me 1,2-dimethyl cyclohexane. Now that we have two substituents on that ring, we have to include the location. We have to build the locant into the name. If it's 1, 2, that simply means that those two methyl groups are right next to each other. Okay? This molecule right here is actually not a unique molecule. All right, this as drawn here would actually represent two distinct cis-trans stereoisomers. So there's more than one molecule that you can draw that has two methyl groups next to each other. All right, so why is that? Okay, let's see if this works. Okay, cool. So I have my cyclohexane here. We see our little hexagon shape, right? I have these two methyl groups that I colored, one in orange and one in green. And the important thing here is that because of that ring structure, these carbons are not able to fully rotate, right? They can't spin around and around and around like they can in a straight chain alkane, which means if I put them on the same side of the ring like this, there's no way for me to bend this ring where all of a sudden they're going to end up on opposite sides. They're always locked on the same side of that ring. Likewise, if I were to pick up one of these green beads, not green beans, all right, and move it over to the other side. Now they're trapped on opposite sides of the ring. And there's no way that I can rotate this bond such that all of a sudden they're going to be on the same side. So because of this ring structure here, our rotations are limited, and so groups are either going to be trapped on the same side of the ring or on opposite sides of the ring. All right, and those are our two different stereoisomers that we can have. In order to represent those two stereoisomers, I'm going to need to use my dashed and wedged bonds. Okay, so if those two groups were on the same side of that cyclohexane ring, I would put them both on a wedged bond or both on a dashed bond. All right, so with those both on a wedged bond here, those methyl groups are locked on the same side, probably no dash, same side of the ring. And again, it can't possibly rotate so that one's on one side and one's on the other. All right, or if I was going to show that they were locked on different sides of the ring, I would draw one as a dashed bond and one as a wedged bond. So these are locked on opposite sides of the ring. Okay, so these are our same, they definitely have the same chemical formula. They have the same connectivity of atoms. They have this ring structure with two methyl groups right next to each other. Where they differ is in the spatial arrangement of these two methyl groups. On one of those structures, those two methyl groups are pointed in the same direction. In the other structure, they're pointed in opposite directions, and you can't convert between the two of them. All right? So these are two stereoisomers. When they're locked on the same side of the ring, this is what we call the cis isomer. And when they're locked on opposite sides of the ring, this is what we call the trans isomer. What's up?
Is the physical property changed?
Ever so slightly, yes. And sometimes very, very barely. But yes, they are different molecules. They do behave differently. Very, very close, but different. All right. So we can sort of note here, both of these would be considered 1,2-dimethylcyclohexanes. So if I'm going to distinguish between which specific stereoisomer I have, I'm going to build that stereochemistry in the name. All right? So this we would call, and we put it out front with a dash, this would be cis 1,2 dimethyl cyclohexane. And this would be trans 1,2 dimethyl cyclohexane. All right, so our ring structures, because of that ring, we're limited in our rotation about those single bonds. So we can either have groups that are trapped on the same side of that ring, either both in wedges as I drew here, or you could have them both on dashed bonds. That would also be the cis structure. Or they could be locked on opposite sides of the ring. Those would be the trans isomer. We build that stereochemistry into the name by putting it out front. All right, so let's do an example here. Just make sure we got this down. Let's say that I was going to ask you to name this molecule here. All right, so first of all, let me just point out, because this group right here might look a little weird. I have this wedged bond, and then I just have these straight lines coming off of it. This is simply how we would show a 3-carbon group that is pointed off of that ring coming out of the page. You show the stereochemistry, rather the orientation of the first bond. From then on out, you just use those straight lines. You don't continue to use wedges if you're going to show multiple carbons. So this is just quite simply a propyl group, a 3-carbon group that's pointed out of the page. My parent chain is, of course, my ring, my cyclobutane. I have a propyl group on that carbon. This would be what? A methyl group with its 1 carbon. I'm going to number my parent chain. Which one am I going to start numbering at, M or P? M, it's a tie. You can convince yourself it's a tie. So I'm going to pay attention to alphabetical order here. All right. So this would be 1-methyl, 3-propyl, cyclobutane. And then I'm going to include the stereochemistry of this molecule here. Since one's on a wedge and one's on a dash, this would be trans. And so again, that goes out front with a dash. So trans dash 1-methyl 3-propyl cyclobutane. Okay. All right, so these squares, these little cyclobutanes here, they're quite rare. I've never honestly ever seen one out in like the wild, out in the lab, all right? And there's a good reason for that. They're not very stable. So let's take a look at this graph here. This graph tells us about the strain energy, or we can kind of simply think of the stability of these rings as a function of ring size, aka number of carbons. So first of all, convince yourself you can't have a 1 or 2 carbon ring, right? That's not going to work out. So the smallest ring that we can have is 3 carbons, a cyclopropane, and those are very, very unstable, very high energy. Remember, high energy is bad. If we make 4 carbons, a little bit more stable, but not much, still very unstable. And then as soon as we get to 5 carbons, there's this massive drop that we see in our stability here. So our 5 carbon rings are quite stable, and then the most stable ring structures are those 6 carbon rings. All right? You can have larger ones. 7 carbons are about as stable as 5. You can go larger than that. We're going to focus on these small ones here and try to understand these big differences in energy that we see in terms of the stability of these ring structures. All right? So what we're going to do is we're going to take a look at a triangle here. If we have only 3 carbons, they have to lie in the same plane. So they would form a perfect triangle, a perfect equilateral triangle. And so what would the bond angle be between our carbon atoms in this perfect triangle here? 60 degrees, right? Well, what does an sp3 hybridized carbon like to have as its bond angle? That 109.5. 60 is quite far from 109.5. So in order to get this ring to form, you have to bend these bonds in a way that carbon is not going to be happy with, right? You are far from your ideal bond angle. This causes a lot of what we call ring strain. Angle strain. All right, non-ideal bond angle. All right, so not only that, but now we're going to do our Newman projection here. We're going to look down one of these carbon-carbon bonds. We can see that our bonds are parallel to one another. What did we call that with our Newman projections? Yeah, these are eclipsed bonds here. And what do we know about eclipsed bonds? Good or bad as a stability, from a stability standpoint? Bad, right? Our bonds don't like to be next to one another. So this is what we call torsional strain. So this triangle here has lots of both angle strain and torsional strain. Again, the torsional strain are those eclipsed bonds. All right, so what makes this triangle so unhappy? It's mad because it has a bad bond angle, and it's mad because its bonds are eclipsed. If we go to 4 carbons, what you'll notice is that it kind of kinks itself a little bit so that it isn't forming a perfect square. That's because it's trying to get to that 109.5, but it doesn't do a great job. This is still around the 90 degrees that you would expect. So a little bit less, but still lots of angle strain. All right, again, by angle strain, I mean those non-ideal bond angles. All right, if we take a look down one of these bonds here for our Newman projection, we're going to see it's a little bit better, but you still have these fairly eclipsed bonds. So still, we'll say quite a bit of torsional strain. And I think this picture is being a little bit generous because if we just go to the numbers here, how much did we relieve that torsional and angle strain? Not much, right? I mean, they're not that much more stable than that triangle is. So we still got quite a bit of angle strain and torsional strain in that four-membered ring. All right, if we go to a five-membered ring, your cyclopentanes, they do not look like a flat, perfectly drawn, what do they call those? Regular pentagon, right? Where everything's in the same plane. Instead, this thing has kinked itself into this little structure here so that it can adopt these relatively ideal bond angles, right? So these do not have, we're going to say no, probably a little bit, but we're going to go ahead and say no angle strain. And if we do our same Newman projection, we look down one of these bonds. All right, if we look carefully over here, we can see that we're very close to our staggered conformation. We're just not quite there, right? So they don't have any angle strain, and they have a little of that torsional strain. So now we're going to get to our six-membered ring here. And again, these very much so do not form regular hexagons. They instead form what we call a chair conformation, and that's what we're going to spend the rest of the lecture looking at, are these chair conformations here. All right, but in our chair conformation, we can note that there is no angle strain. And if we look at our Newman projection, what do we notice about our Newman projections? They're in that perfectly staggered conformation. So not only is there no angle strain, there's also no torsional strain. So that's why our six-membered rings are nice and stable. All right, so this little structure that cyclohexane will kink itself into, this is what we're going to spend the rest of the class period talking about. I don't know where my printouts are. I must have left them in the other room. So what we're going to do is we're going to take a look at these, what are called chair structures. If you look on Chapter 4, under the Chapter 4 introduction, you will find this chair template here. So if you're using an iPad or something like that, you can go and download this PDF here and kind of mark this up. I have printouts. I must have left them in the other room. Let me grab those. All right, that's what we're going to be working with, is these chair templates. so who would instead prefer a paper copy? Okay, so my goal for the rest of this lecture is to convince you that this little chair figure that you're looking at, this little 2D object here, corresponds to those 3D cyclic structures that you see in the middle of the table. All right? What we're going to do is we're going to first just focus. So first of all, this is just 3 copies of this chair template here for you to use on your homework and for different examples. All right, right now we're just going to focus on one of these structures here. So let's ignore all this business for right now. And let's zoom in. Okay. So again, cyclohexane does not form a regular hexagon. Instead, it will kink itself into what we call the chair conformation. This is how it adopts those ideal bond angles and that staggered structure, right? If you held up this little model kit and looked down one of those bonds, you would see that everything is nice and staggered in that structure, all right? So the first thing we want to do is we're going to note that in our chair structure here, every other carbon, which I'm going to color in red here, is sitting at a point or a peak on this drawing, right? A triangle that comes to a point. And then every other carbon is sitting at a valley or at a triangle that's pointed downwards, right? So all my red carbons here, they're sitting at this peak, a triangle pointed up. All of my blue carbons here are sitting at a triangle pointed down. Okay? My red carbons, the ones that are at those peaks, they have a bond that is sticking straight up out of that ring. These are what we call the axial positions, pointed directly up from that ring. Okay, if you want to look at my little model kit here, I have put green marbles at all of those axial positions, right? Every other carbon has a bond that is pointed straight up off of that cyclohexane ring. Okay? On the other side, I have every other bond that are pointed now straight down from that ring. Let's see if I can show it. Okay? So going back to our drawing here, these blue carbons, they also have axial positions, but those axial positions are now pointed straight down. All right, so every carbon in this ring has an axial position. A bond that is pointed straight up or straight down. Every other carbon, they're pointed straight up. Every other carbons are pointed straight down. Okay? And then every carbon also has what we call an equatorial position. These white beads here, a bond that is pointed away from the ring. So on my drawing here, these are now the equatorial positions. So each red carbon has an equatorial position pointed away from the ring. Each blue carbon has an equatorial position pointed away from the ring. All right, so we don't have this perfect regular hexagon here. Instead, we have this chair conformation where we have one bond pointed straight up or straight down and the other bond pointed out away from the ring. Okay, so then what is this business here? What's this little equilibrium sign? And then my other chair conformation. So cyclohexane, just like all compounds, it's not frozen in space, right? This thing doesn't just sit like this all the time. Our bonds are always wiggling about, and they would love to rotate as much as they can. We talked about how their rotations are limited, but nonetheless, they are rotating about these bonds, all right? So what we're going to talk about now are our rotational conformations of cyclohexane, or what's called the chair flip. All right, this is the change in the rotational conformation of cyclohexane. All right, so we talked about those different rotational states of butane as it's rotating about our single bonds. Cyclohexane also has a change in its rotational conformation. It can't go all the way around and around and around its bonds, but nonetheless, it is going to change its rotational state. All right, so again, we're going to make a little graph here. Where we look at the energy of different rotational states, our rotational conformations. All right, so what we start out with is our chair structure. That is our lowest energy rotational state for cyclohexane. So down here at the bottom. All right, what's going to happen is those bonds are going to start to rotate, and they go through this series of different intermediates here until finally we arrive back at another chair conformation, what we're going to call our flipped chair. I don't really care if you know about these intermediate states here. You can look them up. They are well known. The one in the very middle is what's called the boat conformation. But what I'm really interested in is this chair flip, going from one chair conformation to the other. All right, so cyclohexane is going to kink itself, rotate about those bonds in order to get from one chair conformation to this new chair conformation. All right, and one thing I want to be clear about is by chair flip, I do not simply mean flipping the chair over, right? I'm talking about rotating these bonds. So let's look carefully. Again, we have green in which ones do we call these? Axial or equatorial? Axial. And what about the orange? Axial or equatorial? Axial. All right, so now I'm going to rotate these bonds. Now I have my white beads in which position? The axial. And what happened to all those colored beads? They're now in the equatorial position. So that's our chair flip that we see here. All right? So in our chair flip, what happens is our axial bond, sorry. In our chair flip, what happens is our axial bonds get converted in, or rather axial positions get converted into equatorial positions. And our equatorial positions get converted into axial positions. All right. So what we're going to do is we want to figure out what happens here as we go from one of our chair structures to its flip structure here. And the most important thing is keeping track of our carbons. All right? So I'm going to number these carbons here. Carbon 1, carbon 2, 3, 4, 5, 6. And we have to find those same carbons on the other side of our drawing. All right? So importantly, the carbons that used to be at the valleys, the ones that I said were at the bottom of our triangles here, this carbon 1, when the chair flip occurs, now it's going to be at the top, at a peak, right? So our valley carbons get converted into peak carbons. So this is carbon 1 in my chair flip, carbon 2, 3, 4, 5, and 6. All right, and what you want to do is convince yourself that all of those carbons that were at the peaks on the left-hand side are now on valleys on the right-hand side, and vice versa. The carbons that were on valleys on the right-hand side are on peaks on the other side. Which means if I look at carbon 1, this bond that used to be on top was an equatorial position. But now the carbon that's on top is what? An axial position, because again, our equatorial positions get converted into axial positions when this chair flip occurs. Right? So now my top bond is axial, and my bottom bond, which used to be axial, is now equatorial. All right? So we can kind of fill in here all of our axial and equatorial positions on the new side. All right, the trickiest part about this is finding the carbon on the left and matching it to the correct carbon on the right. And the most important thing to note is that, again, if you were at a valley on the left-hand side, you have to be at a peak on the right-hand side. And honestly, you could have picked any one of them as long as you numbered consistently. It wouldn't matter. But the important thing is a valley on one side is at a peak when that chair flip occurs. Because again, we're converting our axial positions to equatorial and our equatorial positions to axial positions. Okay, so why does this matter? What's the big consequence here? Well, let's now take our cyclohexane template, and instead of just labeling positions, we're going to actually put in a different group, right? So in cyclohexane, there are all hydrogens. But now let's look at a dimethyl cyclohexane, one that has a methyl group in the axial position and a methyl group in the equatorial position. We'll say that the rest of these are all just hydrogens. All right, well then now I want you to follow what happens to those two methyl groups after that chair flip occurs. All right, so now I need you to map these two methyl groups. I'll color one in blue and one in red. And I want you to map them onto our chair flipped conformation here. Where do those methyl groups go? Let me actually flip that. All right, so again, my carbon with the blue methyl group is at a valley, and the carbon with the red methyl group is at a peak. Well, that's going to flip when I do my chair flip. So if I number carbons 1, 2, 3, 4, 5, 6, on this side, it's going to be 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6. All right, so that's what happens to my red and my blue carbons. So now let's fill in our methyl groups on that red and blue carbon. Well, if I look on my blue carbon here, on top is that hydrogen, and on bottom is that methyl group. So that's got to be the same over here. On top is going to be that hydrogen, and on bottom is that methyl group. If I go to carbon 2, on top is that methyl group, and on bottom is that hydrogen. Well, they can't trade positions. We're not breaking bonds here. So now my top bond over here is that methyl group, and my bottom bond is that hydrogen. Whoops, there was a 3 here. So in my original chair flip conformation, I had these both of those CH3s were axial. And what about after that chair flip occurred? What happened? Now they're both equatorial. All right, and we'll sort of pick up with this next time, but just to kind of give you a preview of where we're going here, it turns out that when we have large groups like these methyl groups, they prefer the equatorial position. This conformation is actually more stable. All right, these large groups prefer the equatorial position. All right, simply because there's more room. Remember, atoms don't really like to be next to one another. These beads in the equatorial position here, they have more space between their neighbors than the beads in the axial positions. Right? So big groups would rather be in these equatorial positions where there's more room between their neighbors than they would in the axial position where they're closer to their neighbors. All right? And again, we'll kind of pick up with that next time. We'll do a little bit more work with these chair flips. That's good for now. Yeah, go for it.